Okay, so this is the notes for 9-3 geometric sequences and series. It's a continuation from Thursday, 427, and it is 428 right now. And so we are looking at a problem that we had just kind of started to get a little grasp of on Thursday. So the fourth term of the geometric sequence is 125. The 10th term is 125 over 64. We have to find the 14th term, and assuming that all the terms are positive. So we came up with the fact that we could write the general formulas for a sub 4, a sub 10, and a sub 14. And so then my thought is, well, let's take this a sub 4, which I know, which is a sub 1 times r to the third, and let's rewrite this piece in terms of that. So I'm going to write a sub 10 is a sub 1 r to the third times r to the, what would that be? To make 9. We add exponents when we're multiplying, so to the 6th. So if I do this, now I know what a sub 10 is. What is it? 125 over 64. I know what this is because it's a sub 4. Because the question was, why am I making it r to the 6th? Because this is a sub 10, right? Is a sub 1 times r to the 9th, correct? And a sub 4 is a sub 1 r to the third. So I'm putting this a sub 1 r to the third in. It uses the a sub 1. It uses 3 of these 9 r factors. Because remember, r to the 9th is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm writing 3 of them right there, and then there's 6 of them left for right there. Just you with me on that? And I really just 9 minus 3 is 6, is because I add powers when I'm multiplying exponents. So I'm going to explain that right now. I'm in the midst of explaining that right now. So maybe I'll even write this one more time. So that means a sub 10 is a sub 4 times r to the 6th. And the reason I'm doing it that way is because I know a sub 10 is a number, and I know a sub 4 as a number, and then I would just have the variable r that I can then solve. So a sub 10 is 125 over 64, and that's equal to a sub 4, which is 125 r to the 6th. And so then I'm going to multiply each side by 1 over 125. 1 over 125. Those cancel, and so I get 1 over 64 is r to the 6th. And then I can either take the 6th root, or personally, I can notice that 64 is a power of 2. 64 is 2 to the what? 6. And so this is 1 over 2 to the 6th, which is 2 to the negative 6th equals r, or well, I'll make that this way, because 1/2 to the 6th is r to the 6th, so r equals 1/2. And we know r could be plus or minus 1/2, but they told us in the problem that everything is positive as we go through that. So now I know what r is. And I can either find r sub 1, or excuse me, a sub 1, or I can do this same process again. And, you know, that wasn't terribly difficult for me to do. So I would just maybe do it again. So I'm now going to say that a sub 14 is a sub 1 r to the third. And why am I doing that? Because I know that's 125, right? Times r to the what? 10th. So now a sub 14 is a sub 4 times r to the 10th, or 125 times 1/2 to the 10th. And so then in this one, it's to the 10th because I chose to put in this a sub 4, so I did that subtraction again. And so it'll all work out for myself because I never did find a sub 1. I could have found a sub 1, but because now that I know that r is 1/2, I could have backed myself up to find a sub 1, but I was like, I just did this, so I'm just going to do it again. And so 125 over 1 times 1 over, I think that's 1024, yeah. 1024, and so a sub 14 is 125 over 1024. Just a question. The calculators you use, probably if you put that math print thing on or something, do they give you the fraction? Okay, yes, because I did make a note on there that, and so I wasn't sure, exactly if those calculators do that. But I did want to, yep, that is a sub 14. And since I'm multiplying by 1/2, I could divide by 1/2, which is like multiplying by 2, correct? So I could have backed up from this fourth term, which is 125, and multiplied repetitively by 2 to get to the a sub 1. Do you agree with that? Instead of divide by 2, go the other way and multiply by 2. And a sub 1 was, I have that on here, 1,000, I think, right? So I could have done this as a sub 1 times r to the 13th, 1,000 times 1/2 to the 13th. Either answer is the same for that. Then we're going to look at sums of finite geometric sequences. And so I'm just going to put up this slide for the sum of a finite geometric sequence. And so we know what a geometric sequence looks like. And so finite means it ends someplace. And here is our sum written in summation notation from I equals 1 to n of a sub 1 times times r to the I minus 1. And then our formula is a sub 1 having that first term times in parentheses 1 minus r to the n over 1 minus r. And a little headache typing this in. So a lot of times, like that denominator of 1 minus r, I usually just figure that one out. And so I'll give you a moment to write that. Anybody need to see that anymore? Okay, so here is our first problem, and I'll just write it as I go through so I know you have time to write it. So it's the sum from I equals 1 to 12 of 4 times 0.3 to the I minus 1. To start with, yeah, to get that first term. Yep. Uh, so, um, So this is set up so that it's starting, yeah, with 0. Yes. And I would not write these out, although, you know, when in need, you can sure do that. But I would find a sub 1, and so that's 4 times 0.3 to the 1 minus 1. So 4 times 0.3 to the 0, 4 times 1, which is just 4. So a sub 1 is 4. What is r? It's just right on there. What is the, what are we multiplying by to get the next term? Zero point 0.3. R is 0 0.3. And what is N? 12. Okay, so maybe even give yourself some little arrows or something like that to kind of remind yourself what that is. And I would say, you know, just writing the formula every time we use it today will kind of help solidify what that is. So this is the formula for a finite geometric sequence, which is then called a series. S sub n equals a sub 1 times, in parentheses, 1 minus r to the n over 1 minus r. And I wrote myself a note that you should type this in on a calculator very carefully. And so sometimes I chunk that up a little bit so I don't have to do everything all at once. So S sub 12 is a sub 1, which is 4, times 1 minus 0.3 to the 12th over 1 minus 0.3. And I'll tell you that's how I write it to begin with, but then when I'm actually physically doing the problem, what's 1 minus 0.3? 0.7. So generally, I just type in 0.7, and that makes me less likely to make an error. So just take a minute, type it in however you think is going to work, and we'll see what we get as an answer. And I rounded mine to 3 decimal places, S sub 12. You could, yep. And so if you 0.3 in parentheses to the 12th, that's fine. If you do a parenthesis there, the deal is you have to have that numerator in a parenthesis also, kind of, just to. What did you get for this one? 5.714. Okay. So now, did you write this summation formula down, correct? Okay, it is super important that for this to work out the way we just did it, that this is to the I minus 1. And so that means when I put in 1 here, I get 0, this power to the 0 power, correct? So the next thing we want to look at is a variation of this, just to make sure that we know what's happening. So I'm just going to kind of list a couple of terms out for this one that we just did, to just kind of remind us. So this was 4 times 0.3 to the 0, comma, then it would be 4 times 0.3 to the 1, and then 4 times 0.3 to the 2, up to 4 times, what's that last term going to be? 0.3 to the what? Which is it? 11, right? So, so that's what's happening in this situation. And our first term then was 4, and then as we go through and then to the 11th. So look at this next problem, and I have to kind of go to the slide to find it. Okay, so when you're using this formula for the sum of a finite geometric sequence, you have to be careful to check that it's in this form, and that one was correct. Excuse me, it was I equals 1 to 12, a sub 1, r to the I minus 1. And if we have this one, and I have the work just written here, this one deceptively looks the same, but what's the difference about that exponent? Right, there's no minus 1, it's to the I. And so that means that a sub 1 is 4 times 0.3 to the 1. And then R is 0.3 and N is still 12. So you just want to be careful. And if you notice the way that I did that problem, I didn't just announce that a sub 1 was 4. I put 1 in, and when I use that as my strategy, I don't have to worry about if it's to the I or to the I minus 1. I'll know what a sub 1 is. Does that make sense to you? Just to let you know. And look, it's a much different answer as we look at this one, because it's getting lower. So then when we add it, it started lower and it ends up lower as we go. So that should make sense, subtracting 4 from that other answer. So geometric series is the next section. And summation of terms of an infinite geometric sequence is called an infinite geometric series, or just geometric series. So now we're going on forever. So think about this. If I'm multiplying by 2, we'll say, what is going to happen to an infinite geometric series? It's going to infinity. But if I'm multiplying by 1/2, what's going to happen to the infinite geometric series? It well, if it depends on what kind of number I have, but it's not going to go to negative infinity. Let's say I start with like 12. Half of 12 is 6, half of 6 is 3, half of that is 1/2, and then I keep having. What is it getting close to? It's getting close to 0. So the formula for a finite geometric sequence can depending on the value of R, be extended to produce a formula for an infinite geometric series. But what do you think has to be true about R? Well, if it's greater than +1, what's going to happen to those numbers? They're going to just balloon out forever, right? So if I started with 12 and I'm multiplying by 2, that's 24, 48, 96. You know, it's just getting bigger, 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 bigger. So specifically, if the common ratio R has the property that the absolute value of R is less than 1, so it's that fractional thing. If it is negative, it can go to -1, up to -1, but not including -1, and then they'll just oscillate in sign. But if the absolute value of R is greater than 1, it's just going to go to infinity. So here's kind of what happens. So think about the fact that if R is a fraction, R to the n, and we're talking way back at limits again, because, you know, if we move to calculus, we want to have a firm grasp of limits. So if I have R to the n, and R is between -1 and +1, when this goes to a super high power, what's going to happen to this fraction? It's going to go to 0, right? And so we can put that limit in and say, okay, well, that's going to be 0 as n goes to infinity. And then our equation becomes simply a sub 1, because we'll multiply it times 1 minus 0, which is just a sub 1, times over, 1 minus r. So this is the sum of an infinite geometric series only when r is less than 1. So I'm going to pause this a minute and just let you, I'm going to pause this a minute and just let you kind of write that equation. So then, and the other thing just to note to yourself that if the absolute value of r is greater than 1, then as that series goes to infinity, it does not have a sum. And so then here's a couple that we'll find the sum for. So find the sum from n equals 0 to infinity of 4 times 0.6 to the n. And we'll just do these one at a time. I'll just move this b down a little bit so I have a little more room. Okay, so the thing that I would just kind of, I like to kind of think about, and if you're ever not sure if it's going to have a sum or not, you can always write a few terms just to see what's happening term by term. So, there's always so much to remember with these problems that sometimes that might be helpful. So this is 4 times 0.6 to the 0, plus 4 times 0.6 to the 1, plus 4 times 0.6 to the 2 plus dot 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 plus 4 times 0.6 to the n, and just kind of keeping going as we look at that. So this is 4. 4 times 0.6 is 2.4, and then this one is 1.44, and plus, oops, and it just keeps going and going. And so those are getting smaller, and 0.6 is okay to use to find this sum. So our absolute value of r is less than 1, so r is 0.6. A sub 1 is 4, so just by writing a few terms, I kind of figured that out. And then for this one, S sub n equals A sub 1 over 1 minus r. And so 4 over 1 minus 0.6. Ooh, big dot there. So 4 divided by 0.4. And what is 4 divided by 0.4? 10. Yep, it's 10. Yeah, if we think about that a little bit, it should be 10 for us as we go. I try not to use a calculator as a crutch because, but at the same time, when I'm taking a test or quiz, I would always use a calculator, but also just kind of check myself as I go. So this one's written a little bit differently. How do we find R for this one? Divide. What by what? 0.3 divided by 3. And so what is R? Yeah, 1/10. 1/10 or 0.1. And so the absolute value of R is less than, I'll just, not or equal to anyway. The absolute value of R is less than 1, so we're good to go. And what's A sub 1? 3. So S sub n equals A sub 1 over 1 minus R. So A sub 1, 3 over 1 minus 0.1. 3 over, what's 1 minus 0.1? 0.9. And what is that? Yep. So yes. So you can write that correctly as 3.3 repeating, or 3 and 1/3. Please do not round unless you, in this kind of situation, unless you are asked to round as you go. The next one is the last one in this section, and it is about our application problem, and it's about an annuity or money and getting interest. So here, here's our application problem. An investor deposits $50 on the first day of each month in an account that pays 3% interest, compounded monthly, which is like super wonderful. So we're not really getting that right now. And what is the balance at the end of 2 years? This type of planned investment is called an increasing annuity. And so we have to remember the old interest formula. What is the interest formula? That's the P times, nope, one, well, good. So, okay, yeah, so now we kind of, yes, N is 24, and so A sub 1, so we kind of have to think about this as we go. A sub 1 is going to be our first term in this, and so N is 24, I agree with that. So to figure out what our R is here, and by the way, our R in our series is not the same as this R, which is our interest formula. Do you agree with that? 0.03, yeah. So I want to kind of think about this as I go. So A sub 1, or yeah, A sub 1 is 50 times 1 plus 0.03 over 12 to the 1. It's compounded. How often is it compounded? Month. So, okay, so this is the deal. What does A sub 1 stand for? No, the first month. Oh, good question. Oh, okay. Wow, I just have to kind of look my notes over a little bit because I just got myself a little bit confused. Oh, so it is 12, but yes, it's, oops, just a second. So this is one what? Month. So this is one because N is 12, but what's my time? But my time is always in years. So this is 1 month. So it's like times 1/12 of a year, which makes it one. Yeah, because it just I hadn't figured that out recently in my head, so I'm like, why is that one? And that is still 12. Right. Okay. So this is 50 times, what is all that? No. 1 plus 0.03 to the over 12. So it's more than 1, but not much more than 1. No. Yes, definitely. Okay, and the reason I wanted to write it like that is I want to think about this as my first term, right? So, so what is R? R for the series. What's R? This is the R in the series. 1.0025. And so A sub 1 is whatever this is. I don't know. And so our A sub 1, so this is for our series. Our A sub 1 is 50.125. So now we are 2 years, so n is 24. We've kind of established all that. So now are we using our finite or our infinite sum? Finite. So S sub n equals A sub 1 times 1 minus r to the n over 1 minus r. And so S sub n equals 50.0 or 0.125 times 1 minus 1.0025 to the 24th over 1 minus 1.0025. So find it. So practicing typing that in is kind of part of what we have to do. Okay. Okay, so what did you get? Just a minute. Yeah, I know. I talked to you, and I knew it was you, and I was like, oh, I wonder if Riley's having a little trouble. S sub n. So tell me again. 123.23. So this is so make sure you know that this is the balance in the increasing annuity after 24 months. Okay. Wonderful. Okay, so In this part of the year, we have to kind of just make sure that we're meeting our needs. And so this geometric, arithmetic, and just general sequences and series is all we're going to do of Chapter 9 before the final. Because here's the weird thing about SMSU and this class, and that is that on our syllabus that says what's there, conic sections are given um, as an elective topic, but they always seem to show up on the final exam. And so because of that, I don't do the full-blown everything about conic sections, but I do a little bit of an introduction to conic sections, and I'm going to start that right now, and then we'll work on conic sections next week, and I'll have kind of a lesson that I'll have prepared for you the next time. So I'm going to start the introduction to conic sections right now. And the deal is we skip right to section 10.3. And so it's helpful if we do a little introduction to the conic sections that's sort of separate. And after next week, yes, I will, or after next week gets started, so on Monday, you'll have a recording for half of the period, and then you'll have half of the period to work on things. And I decided not to check 9.2 today because you can have plenty of work time to check 9.2 on Monday. And then either Tuesday or Wednesday of next week, whenever I'm kind of ready for that after being gone, I'd like to schedule out the rest of our time. Does that make sense? So you're going to tell me when senior things are happening, and also a little bit about what individually, if you're going to be gone a day or two, so that I can do things. So my goal is to finish up. So I'm skipping around a little bit. I'm doing anything that's on the final first. Then we'll take the final, then we'll finish up with the rest of the items, and then we'll take our end of the quarter test second. Does that make sense? Because I'd rather kind of buffer the things that are just final related, and that no college professor is going to do that way, but because we're in a unique situation and you're in high school and towards the end of the year, it gets to be a lot of things going on. So I've been finding that if we do the final just a little earlier, we're more likely to all be here and ready. Yeah. Mm. Right, right. So don't throw out chapter 9 after this 9.3. We'll be coming back to chapter 9, but I know that 1, 2, and 3 we have to do before. So I'm doing all the required things and then kind of the optional things, kind of. So So you've had your quarter test, and you just have one more test for the, quarter. And so we'll actually take the final first, and then we'll take the end of the quarter test. And then after you've done all that, I do a little bit of time for us just to decide which test you're throwing out. Generally it's the lowest test, as you go through for the SMSU class. So, yeah. Yep. So, so let's take a minute or two, and I'm just going to do this brief introduction because I'm not sure how super well this is gonna come off. So really, these are just things I've gotten off the internet because I feel like in our school district, a weakness we have is conic sections. Conic sections are something that in the state of Minnesota are less emphasized at a high school level. And so I found this nice little introduction since you haven't had anything, and I kind of pieced some things together. So I'll just go through this introduction. I'll probably be finishing the introduction up on Monday when you're here and I'm gone on a recording, and then I'll give you work time. Samantha, did you have a question? It'll be the final exam will be 2 or 3 days. It depends on how much time we have to allot for that. Okay, so the first part of the introduction is on circles, and we've already done circle things and looked at circle formulas. So all of the things that we're talking about are slices out of a cone. So if we had a cone, which you're familiar with, and we just slice it in half, parallel to the base, which is a circle, we would always get a circle. Do you agree with that? You know, so whatever the base is, that circle, and then we get progressively smaller circles till we get up to the point, correct? So that's our first conic section, is just a circle, and that's why they're called conic sections, because they come from a cone. They're kind of the slice of a cone as we look at it. So circles are round, and there are some animations. I'll see if I can put some of those on. This is just a SmartNote file, so it doesn't really have that. But we know that if we wanted to make a circle, we can take a string that's the length of a radius. The green dot is where we would hold our finger to make the center, and then we kind of go around and we can get a circle. And then, you know, this is maybe a little more dangerous, but if we wanted to make it into a sphere, you know, we could kind of swing that, you know, maybe have a little ball on the end and swing it and in space. So, and then we could get a sphere as well as we go through. Oh, I am just gonna look at this, and circles are, but spheres are what is really where it's all at. So slices of spheres are used for all sorts of lenses and optics. And this is a lamp that uses slices of spheres to aim light. And so, you know, spheres are very, very important. So then if you slice the cone instead of parallel to the base, but at a little bit of a diagonal, do you agree you get an oval shape instead? Does that make sense? You know, that would be an oval slice. And that's actually called an ellipse. So have you done any work with ellipses? I don't feel like you have. I didn't say this. I'll back up a second and just call this intro to conics. And so we'll just write a heading right now. And the first conic is a circle, and we're familiar with that already. And this is just kind of naming the circle. And if you remember, we can take x minus h in parentheses squared plus y minus k in parentheses squared equals r squared. We had that formula earlier in the year. And so circles are conic sections that we're already familiar with. The book authors, or the final you'll take from SMSU might also have things that are ellipses and hyperbolas. So if we do this, we get an ellipse, E-L-L-I-P-S-E, and it kind of looks like this oval shape as we're looking at that. And then what we want to know about an ellipse is it has two dots kind of here and here, and for now you can just draw them kind of anywhere, but I'll explain that as we look at this. And those two dots are called the focus. So I focus. I'm going to stop right there. I'll let you look at that, and then we'll continue on next time.